Welcome to Demystifying Math. In this lesson we're going to be discussing geometric series. In the first part of this lesson we came up with two formulas. One was the formula for the terms of the sequence, which is represented by g times r to the n, where g is the first term of the sequence and r is the constant ratio. The other formula that we came up with is for the sum of a finite number of terms of the sequence, which is given by s with a subscript of n. What we're going to do in this video is find a formula for the sum of an infinite number of terms of a geometric sequence. We're going to start with our formula for a finite number of terms for the sum of them and take the limit as n goes to infinity. So looking at our formula, the only term that has an n in it is the r to the n. So we're going to focus in on what happens to r to the n as n goes to infinity. Now you're going to get different values for the answer for this limit based on what r is. So let's start at looking at values of r that are greater than 1. Suppose that r is equal to 3. Then that would give us the sequence 3, 9, 27, 81, and so on. Well, those numbers are going to infinity. So the limit as n goes to infinity of 3 to the n is going to go to infinity. Well, since the numbers in the sequence are heading toward infinity, the numbers in the sum, or the series, must also be going to infinity. Remember, the series is just the sum of the terms of the sequence. So looking at our first term is 3. Our first two terms add together give us 12. The sum of the first three terms is 39, and so on. So this series is also going to have a limit that goes to infinity, or what we say, diverge. Now you can probably imagine that for any r values greater than 1, that you're going to have the terms of the sequence go to infinity, which causes the series to also go to infinity or diverge. So we would say that the geometric series diverges for any r values greater than 1. Alright, so let's look and see what happens when r is actually equal to 1. Well, that's just going to give us a list of numbers of 1s. And that does have a limit of 1. But let's look and see what happens to our series. We're going to sum together the terms, so that just gives us the numbers 1, 2, 3, 4, and so on, always one unit apart. Now the sum is going off to infinity, so the limit does not exist, which means that this series is going to be unbounded and diverges. Let's look and see what happens when r equals negative 1. Well, that's going to give us the sequence of 1s that are alternating in sign, negative, positive, and so on. And what happens here is that the limit does not exist because they're not heading toward any one specific number. Let's look at the series. The series is going to alternate from negative 1 to 0. So the series does not have a limit either, and if it doesn't have a limit, then it diverges. Okay, so far we saw that for numbers greater than 1, it diverges. For r values of 1 and negative 1, it also diverges. Let's look and see what happens for numbers between 0 and 1. Let's suppose that r equals 1/3. Well, that would give us the sequence 1/3, 1/9, 1/27, and so on. What you should notice about these terms is that they are getting smaller and smaller, heading towards 0. So for this one, the limit does exist. It goes to 0. And what we want to do from there is look at our series. So we're going to add together the terms of the sequence. And I went ahead and wrote them in decimal form so you could see that they are approaching or coming very close to 0.5 or 1/2. Let's look at our sum formula. Our sum formula for a finite number of terms was g times 1 minus r to the n over 1 minus r. If we take the limit of that as n goes to infinity, and we know that r to the n is going to go to 0, we can replace r to the n with 0. And that simplifies our formula down to g over 1 minus r for our sum of a infinite number of terms. So let's use the formula g over 1 minus r to get our sum of the infinite number of terms. And you can see that with r being 1/3 and our first term of the sequence also 1/3, we got out 1/2. And just by looking at the first few terms of this series, you can see that our sum is very close to 1/2 already. you should also notice that the last few terms are very close together, not very far apart. So what's going to happen is each one of those sum numbers is going to go closer and closer to 0.5. You should end up with numbers like 0.4999 as you go out further to add additional terms on. Alright, so for this one, it does converge to 1/2. It's bounded by 1/2, and the limit of the sequence was 0. We really need to have the limit of the sequence to go to 0 in order for the series to even possibly converge. Let's look at a number between -1 and 0. Suppose that r equals -1/3. Well, in this case we have an alternating sequence. The absolute value of the terms is the same as what we just saw. So the absolute value of the terms is heading towards 0. And if we look at the terms in the graph, you can see that the odd terms are heading up towards 0 while the even terms are heading down towards 0. So we would say that this has a limit of 0. So that's good so far. Now let's look at our series. We have a formula for our series that we found a little bit earlier, g over 1 minus r. And if we plug into that, we get out -1/4. Remember, our first term of this sequence was -1/3, and our ratio was -1/3. So we had a double negative in the denominator, so it ended up being added there. Let's go ahead and look at the terms of the series, and you can see that we're pretty close to -1/4. Sometimes we're below, and sometimes we're above -1/4, but it's kind of hovering around -1/4. So looking at them on the graph, you can see that better, that they're very close into y equals -1/4, that line. So this one does converge to -1/4, and you can probably try a few more terms, but any r values between -1 and 0 will converge. And we'll use the formula g over 1 minus r to find out what they converge to. Okay, so we haven't looked at any numbers below -1 yet, so let's try r equal to -3. -3 to the n gives us an alternating sequence. And if you look at the absolute value of these numbers, you can see that they're just getting greater and greater. Even if you looked at the evens and odds, the odd terms are heading toward -infinity while the even terms are heading to +infinity. So this limit does not exist. And if the limit does not exist, the series is not going to converge. It will diverge. And you can look at the numbers in the series and see that they are not approaching any specific number. So the limit of the series would not exist. Okay, so far what we saw is that the absolute value of r is greater than or equal to 1. You're either going to have a limit of the sequence that does not exist, or it goes to infinity. So the geometric series would diverge. For r values where the absolute value of r is less than 1, those numbers between -1 and 1, you're going to get the limit of r to the n to go to 0. So the sum of the terms of the sequence are going to converge to a specific number, and that number can be found by using g over 1 minus r. Okay, so let's do some specific examples. Suppose that we had the sum of the numbers represented by 2/3 to the n. Well, this is definitely geometric, and our r value is 2/3. So all we have to do is plug into our formula g over 1 minus r, and we get out 2. Let's change our problem just a little bit and start it at n equals 3. Well, that means that our first term of the sequence is 2/3 to the third. So that would be the value that we're going to plug into the formula for g. Our r value is still our constant ratio of 2/3. So we ended up with 8/9. Now, you could have taken the answer to problem 1 and just subtracted out the first two terms of the sequence. Because we're starting at n equals 3 means that we're not including the first term or the second term. Well, the first term is 2/3 and the second term would be 4/9. If we take that away from 2, we get our 8/9. So you can see how these two formulas are so closely related. Let's look at another example. In this case, we have 1/3 times -2/3 to the n. Well, the 1/3 is a constant, and that can be brought outside of the summation symbol. And then we have a geometric series of -2/3 to the n. We're going to add all those terms together. negative 2/3 is between negative 1 and 0, so it should converge, and we should be able to use the formula g over 1 minus r to find our sum. And multiply it by 1/3. So we have negative 2/15 as our sum for this problem. Okay, let's look at our next problem. We have the sum of n equals 5 to infinity of 1 over 2 to the n plus 3. It doesn't look exactly like geometric. Remember, with geometric, you need some number times your constant ratio to the power of n. Or to a power of n plus 1 or n plus 3 is fine also. Alright, so we have, in this case, we're going to rewrite this. Since 1 to any power is 1, you can rewrite it as 1/2 to the n plus 3. Then I'm going to break that apart as 1/2 to the n times 1/2 to the third. Remember, with like bases, you would add the exponents, so I just broke it up. The 1/2 to the third is a constant, so we're going to bring that outside of our summation symbol. And we end up with just 1/2 to the n, which is definitely geometric. Our constant ratio is 1/2. And since we've taken the 1/8 out, our g value for that is just going to be 1/2 to the fifth, since we're starting with the fifth term of the sequence. And then we'll multiply that by 1/8, so we don't need to make it more complicated by leaving the 1/8 in there. And then simplify that, and we get 1 over 128 as the sum of our series. Let's look at another example. In this case, we have the sum of n equals 1 to infinity of 2 to the n minus negative 3 to the n over 5 to the n. Doesn't look like it's geometric, but let's try rewriting it. The first thing that I'm going to do is break it up as two separate fractions. Now I notice that everything is to the power of n, so I'm going to rewrite them as fractions to the power of n. Now you can see we have 2/5 to the n. 2/5 is between negative 1 and 1, and so is negative 3/5. So they both will converge, and they will both be able to find the sum of both by using the formula g over 1 minus r. So I'm going to work them separately. 2/5 to the n, our first term of the sequence is 2/5, and our constant ratio is 2/5, so we end up with 2/3. With the negative 3 to the n, my first term of the sequence is negative 3/5, and my constant ratio is negative 3/5. So I'm going to add the 3/5 on at the denominator. So we have negative 3/8 as that sum. Now the two sums were subtracted, so we have to subtract them, and we get 25/24. Alright, thank you for tuning in to Demystifying Math.